Hello there and welcome back to this video series on control systems. In the past video, we have specified and defined what is BIBO stability and what is the essential condition for BIBO stability of a system. In this video, we'll try to see how we can determine if a system with a given transfer function is BIBO stable or not, and kind of try to explain the location of poles and zeros in the S-plane and how they affect stability. This we'll try to do with a series of examples, maybe 4 or 5 examples, so that you can relate the math behind and the location of poles and zeros. We'll briefly review the conditions we laid so far and then look into a couple of examples. Okay. If all the poles have negative real part, the system is stable. If the real part of any one pole is positive, the system is unstable. If any repeated poles lie on the imaginary axis, then the system is unstable. If only single poles, single complex conjugate poles lie on imaginary axis, then the system is marginally stable and we have sustained oscillations. With that, we look at example 1, where the transfer function of the closed loop system is given here, 10 into s plus 3 by s plus 1 into s plus 2. If you equate the numerator to 0, you get s is equal to minus 3, which is 1, 0. And in the denominator, you have s is equal to minus 1 and s is equal to minus 2 as the poles. So minus 1, minus 2 are the poles and minus 3 is the 0. Both these poles have negative real parts. In fact, there is no imaginary part associated here with, but we can note that they have negative real parts, minus 1 and minus 2. Because all the poles have negative real parts, the system is BIBO stable. These poles can be shown in the S-plane. The plane on which you have axis real along the sigma axis, imaginary along the j omega axis. This plane is what we call S-plane. In the S-plane, you show the poles and zeros as shown here. One pole at minus 1, 1 at minus 2 and 0 at minus 3. You can see that the imaginary axis, vertical axis, divides the whole plane into two halves. One half on the right hand side all the way up to infinity, and one half on the left hand side all the way up to infinity. These we call right half S-plane and left half S-plane. All our poles are in left half S-plane. Because the poles are in left half S-plane, the system is BIBO stable. Let us consider another example where the closed loop transfer function is given by GS. Numerator equated to 0 gives the zeros as s is equal to 0 and s is equal to 2. The poles are obtained by equating denominator to 0. Thus you have s is equal to minus 1 and the complex conjugate roots, minus 1 plus j and minus 1 minus j. All the poles are in the left half of S-plane, so the system is BIBO stable. Let us again look at these in the S-plane. You have S-plane with right half S-plane, left half S-plane, and we are indicating a pole by x and a 0 by a small circle. You have one pole at minus 1, one at minus 1 plus j, one at minus 1 minus j. You have a 0 at origin and you have a 0 at plus 2. Whether you have a 0 at plus 2 or not, if all the poles are in the left half S-plane, the system is stable, BIBO stable. As another example, look at this transfer function GS of a closed loop system. The zeros are obtained by equating numerator to 0. So you have only 1 0, s is equal to -1. The poles you obtain by equating denominator to 0. We have s square plus 1 and s square plus 2s plus 2. The term s square plus 1 gives 2 poles plus j and minus j. This term gives 2 roots, -1 plus j, -1 minus j. You have poles in the left half s plane, so it is BIBO stable, but you have 2 poles plus j and minus j on the imaginary axis. So this system will exhibit sustained oscillations. You can call it marginally stable. We'll show this on the s plane. This is the s plane, this is entire right half s plane, this is entire left half s plane, and you indicate pole by x and 0 by a circle. There is one pole here, -1 plus j, this is plus j, this is minus j, and you have a 0. Okay, we are not bothered about this 0 here, but all the poles are on the left half s plane except for these two. These are non-repeated, purely imaginary poles, because this is plus j omega, this is minus j omega, there is no real part. These are purely imaginary poles. These imaginary poles contribute sustained oscillations. We still call it BIBO stable, marginally stable with sustained oscillations. As a last example, consider this transfer function s square plus 1 whole square, s square plus 2s plus 2. Okay. The numerator gives zeros, s is equal to -3. In the denominator, you have s square plus 2s plus 2, which gives -1 plus j and -1 minus j. This s square plus 1 whole square can be written as s square plus 1 multiplied by s square plus 1. There are two terms which are s square plus 1. So one s square plus 1 quadratic term gives plus j and minus j. Another term, another s square plus 1 will give you again plus j and minus j. So we say there is a repeated purely imaginary pole at plus j, because there are two things. This plus j is repeated. Similarly, this minus j is also repeated. If you have such repeated purely imaginary poles, repeated more than once, the system is unstable. We'll try to show it on s plane once again for completeness. We have s plane with real axis, imaginary axis. This is complete right half s plane. This is complete left half s plane. We indicate poles by x, zeros by 0. So you have one pole here, -1 plus j, -1 minus j. You can see that at plus j omega, you have 2 poles. Similarly, at minus j omega, 2 poles. Such poles which exist at a point more than once are called the repeated poles. So there is a repeated pole here at plus j. There is a repeated pole here at minus j. Such repeated poles on the imaginary axis are what makes the system unstable. So this system is BIBO unstable. With that, we give the summary. Stability of a system can be inferred from location of poles. If any of the poles lie in the right half s plane, the system is BIBO unstable. If repeated poles lie on the imaginary axis, the system is BIBO unstable, as we have seen in the previous example. If a single pole lie on the imaginary axis, that is simple conjugate purely imaginary poles lie on the imaginary axis, the system is still, we can say the system is still BIBO stable, but you will have sustained oscillation. If all the poles lie in the left half s plane, the system is BIBO stable. And I think that's all we have for now. Have a great day.